Reinforcement learning, RL, can be applied to the selection of inventory policies by treating the decision-making process as an agent, algorithm, interacting with an environment, inventory system. The agent learns through trial and error, improving its decisions over time by maximizing rewards. Here's a structured approach to applying RL for selecting inventory policies. Key components of RL for inventory policy selection. Agent, the decision-making algorithm that selects the inventory policy. In this case, the agent could choose between different inventory policies, for example, economic order quantity, EOQ, continuous review, periodic review, just-in-time, JIT, based on observed data. Environment, the inventory system that the agent interacts with. This includes real-world constraints like demand fluctuations, lead times, holding costs, and stockouts. State, the state represents the current situation of the inventory system, such as 1. Current stock level of the product. 2. Forecasted demand. 3. Holding cost, order cost. 4. Lead time. 5. Safety stock level. 6. Service level action, the action taken by the agent, which in this case, would be selecting an inventory policy for the product at each decision point. The actions could include 1. Selecting a policy, EOC, continuous review, Q, R, periodic review, P, S, or G. 2. Placing an order based on the selected policy. Reward, the reward is a function that tells the agent how good its actions are. In the inventory context, the reward could be based on the following. 1. Minimization of total cost, ordering cost plus holding cost plus stockout cost. 2. Maximization of service level, for example, avoiding stockouts. 3. Balancing the trade-off between ordering too frequently and holding too much inventory. Policy, the policy is the strategy the agent follows to make decisions. Over time, the agent learns an optimal policy that maximizes the expected cumulative reward. Objective, the agent's goal is to minimize costs, ordering, holding, and stockout costs, while maintaining an adequate service level by selecting the optimal inventory policy over time. Steps to implement reinforcement learning for inventory policy. 1. Define the states. The state of the inventory system can be represented by a vector containing variables like 1. Current inventory level. 2. Forecast demand. 3. Order quantity, if any. 4. Lead time. 5. Service level. For example, state equals inventory level, forecasted demand, holding cost, lead time, order cost, current policy /text state equals /text inventory level /text forecasted demand /text holding cost /text lead time /text order cost /text current policy state equals inventory level, forecasted demand, holding cost, lead time, order cost, current policy. 2. Define actions. The actions would be the selection of an inventory policy. 1. Action 1. Use EOC policy. 2. Action 2. Use continuous review, Q, R, policy. 3. Action 3. Use periodic review, P, S, policy. 4. Action 4. Use just-in-time, JIT, policy. 3. Design the reward function. The reward function should reflect the goal of minimizing costs while ensuring a good service level. For instance, 1. Reward equals total inventory cost, where the total cost is a combination of holding cost, order cost, stockout cost. If demand exceeds available inventory, a negative reward could be assigned for stockouts, encouraging the agent to avoid them. 4. Learning process, exploration and exploitation. The agent needs to explore different inventory policies for various states and learn from the results. Common RL algorithms for this include 1. Queue learning, the agent learns a queue table, which stores the best action for each state. 2. Deep queue networks, DQN. For more complex states, high-dimensional, deep learning models can be used to approximate the queue values. At each time step. 1. The agent observes the current state, inventory level, demand, etc. 2. The agent selects an action, an inventory policy, based on its current knowledge, exploit, or explores new actions, explore. 3. The environment responds by showing the next state and giving a reward, for example, cost savings or penalties. 4. The agent updates its policy based on the reward and continues. 5. Training and convergence. The agent learns the optimal policy by interacting with the environment over many iterations. Over time, the agent identifies which policy minimizes costs and ensures adequate service levels across various demand patterns and uncertainties. Example workflow in a simulation environment. Let's break down a simplified simulation in which the RL agent selects an inventory policy over a period, say 100 days. Initial state. 1. Current stock, 200 units. 2. Forecasted demand, 20 units/day. 3. Holding cost, $0.5/unit/day. 4. Lead time, 7 days. 5. Order cost, $100 per order. Agent chooses action. 1. Selects policy, for example, EIC environment response. 1. New demand for the day, 18 units. 2. Stock reduces to 182 units. 3. Based on EIC, agent places an order when stock hits the reorder point. Reward. 1. Holding cost equals 50 cents times 182 units equals $91. 2. If order is placed, ordering cost equals $100. 3. Total cost for the day equals $91 plus $100 equals $191. This becomes the reward for the agent, with the goal to minimize it. Agent updates knowledge. 1. Agent learns whether its action, policy selection, was effective in minimizing costs. 1. It uses this experience to refine its future policy decisions. RL model training. The agent is trained over several simulation runs. Each run simulates a fixed number of days, with varying demands and conditions. As the agent explores different policies, it gradually converges on an optimal strategy for selecting the best inventory policy. Example use cases for RL and inventory policy. 1. Dynamic demand patterns. RL can adapt to changing demand patterns over time, learning the best policy dynamically. 2. Multiple products. The agent can simultaneously manage policies for a range of products, each with its unique demand and cost structures. 3. Lead time variability. RL can be useful in environments where lead times are uncertain, helping the agent learn when to place orders to minimize the risk of stockouts. Reinforcement learning, with its adaptive nature, offers a powerful tool for inventory policy optimization in complex, dynamic environments. It provides a way to automate decision-making for a system that constantly learns and adjusts to reduce costs and maintain service levels effectively.